Welcome to the spotlight video of the recently published IEEE Transactions on Robotics paper called Coordinated Search with Multiple Robots Arranged in Line Formations, written by myself, Andreas Kolling, and my co-authors Alexander Kleiner and Stefano Carpin. Line clear lives in the guaranteed search problem domain, which at its core is really all about contamination, which represents the possibility of a target being in your environment. You want to clear all of that contamination by moving your sensors and extending the boundary between clear and contaminated areas. With that, you can guarantee that you detect all smart, fast, and omniscient targets. You can maintain that boundary any way you like, from above, from below, in 2D, 2.5D, or 3D, as long as you can guarantee that your sensor footprint covers that part, but you need a 2D model of the environment. At the core of the paper is a line-based approach, based on limited range sensors, which you see on the right, so you need very large teams that sense on these line formations. This is in stark contrast to the left-hand side, visibility-based specification, where one robot can potentially maintain very many boundaries between clear and contaminated areas. In our approach, we need multiple robots to maintain one boundary. We get more control over the shape of the sensor footprint, but we have different challenges in the computation of good motion strategies. So you could take potentially a 2.5D environment, model the sensors in there, and turn it into a 2D representation, and then try to run coordinated strategies in 2D. To give you a sense of the problem, let's look at how an optimal strategy might be executed. You have 3 robots on a line clearing the bottom part. At the intersection, they need 3 more robots to split into the left, and they continue onto the left and right towards the most narrow part. Now we have to choose where to continue. They're continuing on the right first, move to the narrow part, then clear the left with the remaining robots. Now you need 7 robots to finish that last step, and then on the right hand side they clear the largest room with 7. The key questions here are where to block and where to clear, when to go left and when to go right, and we can model that with an optimal. We can also consider scenarios in which the robots have very limited knowledge of the environment. Here they are just working with distributed control and distributed sensing with no map of the environment, so they hit these obstacles unexpectedly, and they have to coordinate the splits without knowing exactly what the optimal split is and how the rest of the environment looks like. So they're exploring the environment, creating a topological representation, and may have to recompute their strategy. Now, the core contributions of the paper are formal problem definition of line clear, NP-hardness proofs, and optimal solutions for simply connected environments. We also provide some fast heuristic solutions and compare these in a computational evaluation to the optimal solution. The optimal solution is obviously quite a bit better for larger environments, costing you dozens of robots less, but you pay a few more seconds in computation time on a regular laptop for fairly large environments above 400 vertices. But 20 seconds to wait for a very large mission isn't the very highest price to pay. See you at the booth.